Okay, in this section we're talking about relative motion, and when you talk about the word relative, it's what are you related to, and this is going to be what we call frame of reference. And they give the definition there at the bottom. Frame of reference as compared to your observer. You can have multiple frame of reference, but it's the observer, and the observer can be in multiple different places. And the example they're given is if you're moving at 80 kilometers per hour north and a car passes you going 90, to you the faster car seems to be moving north at 10 kilometers per hour. So if they pass you, when they say pass you, what direction is the 90 kilometer per hour car going? I heard two different things. I heard south, and then I heard same as you, which would be north. North. So in this direction right here, even though they didn't specifically, well, they in the second bullet they do, but they're talking about standing on the side of the road. We're going to talk about how many of y'all actually drive right now? Okay, so most of y'all. And if not, because again, the reason why we say we add it, how many of y'all have ever been going down the road, say you're doing 50 miles per hour, and somebody's coming at you from the opposite direction, and without giving an actual speed of the other person, especially dogs that aren't used to being in cars or in backs of truck, when a car passes them, what does that dog do? Usually jerks, it's kind of like, whoa, what was that? Because, for their frame of reference, especially if they're inexperienced with other moving vehicles, they look like they're going to be moving much faster. And how many times have you been driving down the road and somebody does pass you in the opposite direction and your car shakes? Okay? Those people are really booking it at that point. So when we talk about adding because of this opposite direction, you've probably experienced that before yourself. We've already seen a video like this before. It's talking about the stunt dummy being dropped from a plane. Do y'all remember seeing the video?
Yeah.
Okay. Again, they're looking at frame of reference here. So in part A, if it is viewed from the plane, let's say you're the pilot in the plane and you drop the stunt dummy, there at the top it looks like the dummy falls straight down because it's your frame of reference. But in the lower part, let's say that you're standing, it looks like it's dropping into water. So let's say you're standing on the land and you're watching this plane go by. What type of motion does it have? Well, it's falling in a different, falling at an angle, so it does look like it has parabolic motion. And this video is going to describe what we're seeing.
When you measure the velocity of an object, your results depend on your own...
Let's try that again.
When you measure the velocity of an object, your results depend on your own motion as well as the motion of the object. Imagine a plane flying overhead, dropping a crate. If you're standing on the ground, the crate will be seen to move sideways at the plane's velocity while falling down. However, if you measure the crate's motion from the airplane, it does not move forwards or backwards from your point of view. The crate falls straight down in this frame of reference. To really understand this, pretend that you are in a completely vibration and wind-free airplane. You might have no idea you are moving if there was nothing nearby to compare your motion with. No frame of reference is special or preferred over any other. Therefore, all motion is relative. When you measure an object's velocity, you are really measuring its velocity compared to your own. All motion is relative.
So when we look at this, and we're going to look at, it's important that you look at the subscripts that are on these, because that's what we're going to focus on. They give an example here. The SE is the slower car, the FE is the faster car. The E part, all of this is with respect to Earth, so they're giving you For the slower car, it's doing 80 north. For the faster car, it's doing 90. And when you write the equation in terms of S's and F's and E's and all this other good stuff, if we look at it, it says VFS. F is fast, S is slow. If you're asking for what's the velocity of the slower car with respect to the faster car, you need those two subscripts together. So notice how they placed these two. If you were to meld or mesh those two together, your E's, that's at the end of this one, at the beginning of the next one, so they cancel out. That's how they get F and S together. So no matter what type of subscripts you decide to use, I don't care if you're dealing with a turtle and you put a little T for turtle and it's the slower one, okay? Or the bobcat, B for bobcat, and it's the faster one. Whatever you decide to put. If you want your final answer, the velocity of the fast with respect to the slow, this is how you need to put it here. And on this next slide, they're showing you, well, what's going to happen if, say, the direction changes on you. In this one, it says the observer in the slow car perceives Earth as moving south at a velocity of 80 kilometers per hour, while your stationary observer on the ground views the car as moving north at a velocity of 80 kilometers per hour. What did they do from the left side to the right side? What'd they do? Why is the negative there? What did they do to put the negative there? What else changed? Look at your subscripts. They went from ES, so that's Earth respect to your slower car. So if they wanted it slower car with respect to Earth, then if you flip your subscripts, talking about who is your point of reference here, then put the negative on the front. So they're talking about solving the problem as we talked about. I already told you, if you're going in the same direction, you're going to subtract. They're just showing you with respect, if you put individual subscripts in there for each object that you're talking about, is it positive or negative? This one, A and C, are your two objects here. This is very generic. Notice that your B's will cancel the way it is written, and A and C will be put together. So as you're working out your problems tonight for homework, keep that in mind. Use your own subscripts. If they're moving in the same direction, we're add. If it's in the opposite direction, same direction you subtract, opposite you add.
Car passing a slow car on the highway. The fast car is traveling at 70 kilometers per hour, and the slow car is traveling at 40 kilometers per hour. It is easy to see that the relative speed between the fast car and the slow car is 30 kilometers per hour. That is, a passenger in the slow car who didn't realize that his car was moving would see the fast car coming up from behind at a speed of 30 kilometers per hour. For simple situations like this, common sense will usually give the right answer. When things can move in 2 or 3 dimensions, however, the subscript method is useful. First, write the velocity of the fast car with respect to an observer standing still on Earth as v sub fe. Next, write the velocity of the slow car with respect to an observer standing still on Earth as v sub se. In a moment, we will need to know v sub es, which is just the opposite of v sub se. It refers to the velocity of the Earth seen from the perspective of a passenger aboard the slow car. Since it is the opposite velocity, we give it a negative sign. If you want to determine the velocity of the fast car with respect to an observer on board the slow car, that label would be v sub fs. This equation will find that relative velocity. Notice that the first subscript of the first term on the right and the second subscript of the second subscript on the right make up the subscripts on the left. The middle two subscripts on the right agree. This allows them to disappear from the answer on the left. In this way, we can show the result we expected. Notice we could construct v sub sf, the velocity of the slow car with respect to the fast car, in the same way. Remember that v sub ef is the opposite of v sub fe. If we are trying to find v sub sf, write a term with the s subscript first and then finish with the f subscript. Once again, the middle two labels of the vectors we are adding must agree. This velocity is found to be negative 30 kilometers per hour. It is the opposite of the previous relative velocity we found because it is from a different frame of reference.
Any questions there? It what? Okay, guys, let's look at this. The first one that we're going to work out is number 3. 4 is a little bit more difficult. So, starting with number 3. It gives you a ferry's crossing a river. If the ferry is headed due north with a speed of 2.5 meters per second relative to the water, and the river is 3 meters per second to the east, what will the boat's velocity relative to Earth be? And it even tells you, remember, if you're finding velocity, you've also got to give direction. So once you find the magnitude of the velocity, you also have to give the angle at which this is going. Write down the important information there. 2.5 meters per second, and then the river is 3 meters per second to the east. So if I were to draw this out, we've got the ferry is crossing the river north with a speed of 2.5 meters per second. And then you've got the river is actually moving east at 3 meters per second. So we've got velocity of our ferry, we're just going to call it a boat. We've got the velocity of our boat. And then we've got the velocity of the river itself. And it wants the velocity of the boat relative to Earth. This is what it's asking us to find. Yeah. Velocity of the boat relative to Earth. So we've got velocity of the boat with respect to the river, and then you've got the river with respect to the Earth. That is 2.5, and that is 3. The math here is supposed to be really simple. How are we going to find the hypotenuse? Pythagorean theorem, okay? So velocity of the boat with respect to Earth, that is 3 squared and then 2.5 squared. Do your math. Velocity of the boat is 3.9 meters per second. And then if we want to find the angle, how are we going to find the angle? Okay, you got multiple options. If you do tangent theta, tangent is opposite over adjacent, and your angle will end up being 50.2 degrees. How would you describe the 50.2?
East of north from east.
Okay, east of north. I'm going to go and give y'all your homework, but I'm going to show you one more example that might help you with your homework. Okay? Because all of this is being podcasted, so it's not going to matter. That fourth one, talking about the pet store, I will work through that one because you're not dealing with a 90-degree angle there. So do you remember us breaking stuff up into components? That's what has to happen on 4. I will work out that one on the podcast once y'all go. Okay, I'm going to finish up example 4 for you. It's talking about a pet store supply truck moves at 25 meters per second north, and then the dog inside the truck moves at 1.75 meters per second at an angle of 35 degrees east of north. What's the velocity of the dog relative to the road? So if we draw this out, it's going to look like this. You've got the truck is moving at 25 meters per second. And then you've got the dog. It says the dog is actually moving 35 degrees east of north. So if I continue out my north line, that is the 35 degrees that we're talking about. And this isn't proportional, but again, it's to get it on here. And what you're going to look for is the velocity of the dog with respect to the road itself. So V sub dr. Notice we don't have a 90-degree triangle here. So we're going to have to look at a few different pieces. I'm going to take this top piece first. This is what I'm drawing in pink. So if I look at what is in pink, I know that I've got my angle right here is 35 degrees. And that dog was also moving at 1.75, so I can go ahead and label my hypotenuse as 1.75. So if I solve for my x and my y component of this part, we'll do sine theta first. Sine theta is opposite over hypotenuse, and this is going to find us our x leg. So sine 35 is equal to x over 1.75, and our x leg is 1.00. If you do the same thing for the y leg of this, you'll do cosine theta and work that out. That's adjacent over hypotenuse, so that is y over 1.75, and your y part of that ends up being 1.43. 1.43. The next piece that I'm going to look at is the lower part of this. So if I break up this triangle to look more like this, okay? I know that my y leg of this is 25. I now know my x leg, okay? That is 1, and we're trying to find the hypotenuse there. Oh, I'm sorry, I did draw part of that wrong. Erase this part here, and that will move all the way up. Okay? So this is V sub dr that we're looking for. You can do the Pythagorean theorem here. We know both legs. There is the y leg, there is the x leg, and you solve for the velocity of the dog with respect to the road, and that ends up being 26.4 meters per second, so it really doesn't change any. And then if you also wanted to find the angle of the dog, because I believe it said to find both, theta, do your tangent theta here. Opposite over adjacent, opposite is 1, adjacent is 26.43. Again, I've rounded some there. So the angle is only 2.17 degrees, and that is going to be east of our north line. East of our north line. You need to make sure that you can still work out different vectors that are given where you're not dealing with a 90-degree angle. You still have to be able to resolve what is given into its components so that you can work with SOHCAHTOA and whatever else is needed that can be at 90 degrees. These type of problems will not go away.